Okay, any questions about the Gaussian?
No, sir.
Okay, in the last 10 minutes, let me do something very, very exciting. Let me just tell you an application of statistical ideas in physics, and and also the introduction of a very important statistical idea, stochastic idea, which is application both in physics, mathematics, as well as the stock market, economics, climate change, all kinds of stuff. So this is a very interesting idea, and the idea is that of a random walk. Okay, what is the idea of random walk? So the random walk is basically, in Western countries, it's described as a drunk person who is, who doesn't know where he is going, and at each step, he or she takes a step in a random direction. So, the first, and then, the second step, so, sorry, it's not. And the idea is that after n steps, what is the probability that the person who started, say, at the origin of your plane is going to end up in a particular point on your plane? Okay, so this is the problem of the random walk. But today we are going to do a one-dimensional random walk. Okay, so a one-dimensional random walk is we have a line and we have the origin, and a point or a walker starts at the origin at time 0, and at each time step the walker can go either right or left with probability. If the walker goes to the right, it has like, it can go to the right with probability P or go to the left with probability Q. Okay, and P plus Q is 1. And the question is that, after after n steps, what is the probability that this walker will be in a particular place? Okay. So let me just let's look at it some in a way. So we are going to say that it took a total of n steps, and we are going to think of each time step as tau and each step length as L. Okay. So it n steps, suppose it goes to the right n1. So n1 right, right steps, and n2 left steps. Okay. Then n1 plus n2 is n. So the probability that after n steps, the walker has taken n1 steps to the right, doesn't matter how, is given by the probability of a particular way that the walker has taken the step to the right times the total number of such possibilities, which is given by n, choose n1. So we see the binomial distribution cropping up naturally here. Okay. So, and then of course, if we say, okay, what is the total probability after n steps, then we have P of n, n1, we sum over n1, n1 goes from 0 to n, then of course we are just going to get, P plus Q to the power n, which is 1. So we can change these variables slightly, and we can say, okay, let's look at small m, which is the number of right steps over left steps. Then, m, and then we can express P n of m. We have factorial n divided by n plus m by 2 factorial, n minus m by 2 factorial. This is very easy to work out. P to the power n plus m by 2, q to the power n minus m by 2. Okay? Now, suppose that tau and L are very small. Then we can show that, this is basically a kind of, this statistical process describes diffusion, right? Because what is diffusion? Diffusion, so suppose you have a little droplet of colored liquid in suspended in water. If the droplet is very small, then it's going to, that droplet of liquid is going to feel a net force on it at any given point in time. So this is known as Brownian motion, and this was key in discovering the atomic, establishing the atomic hypothesis. And so basically, the limit of this thing, of the random walk gives you the diffusion equation. Okay. So the question that we want to ask is that, what is the probability at step n plus 1 that the walker is at position n? Well, it's going to be this thing. And of course, for the walker to be in position m, the walker has to be in the previous step, that is the n step, in position either m minus 1 or in position m plus 1. If the walker is in position m minus 1, then its probability of going right is small p. If the walker is at position m plus 1, its probability of going to left is q. So this is the fundamental stochastic equation, right? And now what we're going to do is that we're going to take tau and L to be small. And we just know that for p n plus 1, m minus p of n of m divided by tau, this is, in that limit, is just that time derivative of p. Okay, not rho, sorry. Let me just not write it as rho, it's p. Okay, and you can also show that p, and I'm just going to drop the n now, m minus 1 plus p, m plus 1 minus 2 p of m divided by L squared. This is in the continuous limit, this is the second derivative partial with respect to space. Okay. So now if I use these two guys, and then I leave it as an exercise, you can add something to both sides and use these, and then you find that, well, we can do this. We have just 1 second. You multiply, yeah. So we set p equals to q equals to half. If I set p equals to q to half, that equation becomes 2 times p n plus 1 m equals to p of n m minus 1 plus p m plus 1. And and on the left hand side you can subtract p of n of m, and then you have to do the same here, 2p of n of m. And then if you divide by the proper factors of t and L squared, you get on the left hand side, and then you get a diffusion constant on the right hand side, and then del squared p by del x squared. Okay, and the diffusion constant is L squared divided by 2 tau. Okay, so random walk is related to diffusion and the continuous, and such a like a process where the probability of the state of a system at some step n plus 1 depends entirely on the configuration of the system at the previous step. It has has a name, and it's called Markovian process. Okay, so the stock market can be thought of as Markovian. I think so. I'm not an expert on that, but quantum mechanics definitely is. In fact, the Markovian point of view in quantum mechanics leads to the path integral formulation of quantum mechanics, as was shown by Richard Feynman. Anyway, we will get to that some other time, but I think we have run out of time for today. And what I want to do in the last few minutes is to actually take your attendance, okay? If I can find the attendance file. But in the meantime, does people have questions?
I do. I have a kind of a digression question. I didn't want to ask it in the middle.
It's okay.
Uh, the moments in statistics, I knew that there were such things such as that. Are they related to electric dipole moments in any way? In
Well,
similar
yeah, their
structures?
function is the same, yeah. But in statistics, but that's more so yeah, they're basically the same thing. And they're we call them moments in analysis. They're called, they are related to what you called, what is it called? They're essentially the different terms in the Taylor expansion of a function, right? I mean,
I also noticed that electric dipole moments come from Taylor expansion as well.
yeah, exactly. So what you're saying is that you have a set of data, i.e. a function. So to specify a function, you need an infinite amount of data, right? If it's some random function.
Yes.
So you basically have to know all the terms in your Taylor expansion. So, but in statistics, we have some set of data. We don't want ignorance is bliss. We don't want all the information. We just want to extract the important information so that we can make money. And so that's why we just like extract these important information such as the average, the variance, the skewness, the kurtosis, so that we have just the right information. We're extracting the right information from the probability distribution. Okay.
I see. Thank you.
Okay.
Sir,
So
Sir, I have a question too.
Yeah.
Is the Maxwell-Boltzmann distribution just like another kind of Gaussian distribution, or there
It's
are?
not a Gaussian distribution. Yeah. It is not a Gaussian distribution. It is the Maxwell-Boltzmann distribution.
Oh, okay.
In physics, you will get other distributions because because of we will see why. That's the whole point of this course. Okay.